All right, welcome back, everyone. Hopefully, everyone has done well on the exam. We're now into December, and we've got very little time left. It is all the things we got to cover. These last two chapters here, they go together very well because this is all about polymers, talking about the molecules, the structures, the common polymeric materials, how they're made, all of that. So polymer, the word, means many repeat units. What this is especially in the case of polyethylene, it's one of the most common plastics that covers most materials that we use. There are a lot of applications of PVC and other vinyls. There are also a number of applications where things like polypropylene are included. And the main differences are that this unit that repeats has a substitution, in this case, chlorine, hence the chloride. Vinyl, because of its location, that's things you'd learn later in organic chemistry, but you guys probably aren't going to be taking that, so that's okay. Propylene adds methyl groups in place of the hydrogen, so forming the beginnings of branch chains that in other polymers become much longer. So polymers are all around you. You've used them whether you understood that you were or not. Ancient polymers include wood, cotton, leather, rubber, wool, and silk. All of those are natural polymers. So rubber coming from the rubber tree. The oldest known uses are things like rubber balls used by the Incas. That was this cool game where they played it with their hips, and then I think it was actually the winning team got sacrificed to idols or something. So if they were to do that today in basketball, it would be a much more entertaining sport. But apparently that's not going to happen. So Noah used pitch, a natural polymer, for the ark, and there's a lot of other examples of this. They've been using pitch and all sorts of things to seal up the gaps in wooden ships because as the wood gets wet, it changes shape and does all sorts of things, and it's very hard to build with wood and have zero gap anywhere. So they would use rope and pitch to fill those gaps. So very, very interesting. The composition of polymers, most of these polymers are hydrocarbons, meaning they have hydrogen and carbon as their primary components. The saturated hydrocarbons typically are what polymers are. There are instances where polymers are unsaturated. So vegetable oil, for instance, is a good example of an unsaturated polymer. Those are unsaturated fatty acids that are chemically very similar to these polymers. When they add hydrogen gas, they bubble hydrogen gas through that oil. It forms a milky white solid that you know as margarine. And they add butter flavoring and all kinds of other things to make it seem like it's a real food, even though it's technically not what it is advertised. So the ethane example here is that each carbon is bonded strongly to 4 other atoms. So this is a single bond. If it wasn't bonded to 4 other atoms, there would need to be a double bond somewhere in there. And ethane is the base molecule for many, many, many polymers as a result of that. There are instances where polymers have intermittent or continuous double bonds, but we're not going to talk too much about those in the course of this. So methane is often used as a starting syngas, meaning synthesis gas, to make polymers because of its ready availability. So there's some interesting areas for the way that these work and operate. Ethane is another common starting point. So polymerizing ethane is fairly common. Propane can be another one that's used. But the difference between these is just looking at the carbon chain. The name changes as you add a carbon, but they're kind of the same thing in that they're carbon bonded to 4 other atoms, one of which will be a carbon, another of which will be hydrogen, or a couple of which will be carbons. In the case of like the middle ones at the center, butane, they get longer and longer chains. So it's the same thing, just with more carbons and hydrogens in a line. So all the way up through all of the anes, and there's a gosh awful lot of anes. So they go way up there. I could give you names that would sound utterly made up and ridiculous, and yeah, they can exist under certain circumstances. So double and triple bonds. The last, before we jump ahead, one of the key properties to understand is the boiling point changes as the chain length increases. That trend is important because polymers have higher boiling points that are generally things like above room temperature. So these are gases all the way up to pentane. If you've used butane in a lighter or something like that, or you've transferred butane, you know that it does evaporate. It gets kind of cold. Pentane is borderline. Hexane is actually a liquid at room temperatures, typically. So 36C, pentane and hexane both are going to be even in Phoenix. 36C is warmer than room temperature. So you're going to be typically liquid for those two. The rest are going to be gas phase. So 4 carbons and less, gas phase. 5 carbons and up are going to be liquid phase, getting progressively heavier and denser with progressively higher boiling points. So think octane, 8 carbons and double that number plus 2. So double that number, 16, 18 for octane, 18 hydrogens. Yeah, all kinds of interesting things. Double and triple bonds are a little bit more unstable because they can fairly readily form new bonds. It has to do with the mathematical geometry that the electron clouds start to form and follow with regard to those molecules. So there's double bonds in ethylene or ethene. Both are the same thing. They're 2 different names from a couple different schools of study, but ethylene and ethene are the key. So an ane, A-N-E, single bond, ene, E-N-E, double bond, yne, Y-N-E, acetylene gas is what this is often called, but it's actually ethene, which is a little bit different. So this is ethene and this is ethine. And the acetylene gas is triple bond carbon. The reason that acetylene is so reactive and burns so readily is it wants to form bonds with, in that case, the oxygen and create CO2 and leave off some water vapor as well. So they can be very, very highly reactive. So isomerism is another kind of important principle where 2 compounds with the same chemical formula can have very different structures. So here's an example for normal octane. Yeah, so there's your 18 hydrogens. I forgot they included this as an example. So the normal octane as a single branch, and they give you a simplified formula of 6 CH2 repeat units and 2 CH3s or methyl groups at the end. And then you have a couple variations when you start changing the way that those are shaped, or you change where there's CH3s, you add another methyl group in the middle, and move one of those carbons around. You rearrange it, and now it becomes 2,4 because it's at the second and fourth position. So second, 1, 2, no matter how you count, 1, 2, and 3, 4, fourth position is a branch, dimethyl hexane. So one methyl group, one methyl group. You wouldn't say a carbonyl group or something like that for these. You just say it's a methyl group because you want to go along the longest chain possible, which would be to this one. So the base being 1, 2, 3, 4, 5, 6 for hexane. So 1, 2, 3, 4, 5, 6, and 2 branches. So 2 and 4 dimethyl, 2 methyl groups, hexane. So the names of these things are important to describe what it is that their geometry is. The free radical polymerization, this is a fairly common mechanism. This is a mechanism that is induced by UV often, and things of that nature, is formation of free radicals, knocking electrons out of their orbit and causing them to stray into other molecules. And the mechanism there enables that free radical comes into contact with a monomer, and then it basically shoots one of the electrons off into oblivion there, and so this becomes a radical. So it is a chain reaction because it forms another radical, forms another radical, forms another radical, forms another radical. So you keep getting this chain of repeats. The chain gets longer. This comes around and does this cycle again and again and again and again and again and again and again until it stops because of running out of reactant more often than not. Or it finally has a collision. Enough of the molecules finally have a collision insufficient to continue, which statistically shows up close to the same time sometimes for when the reactant starts running low. So when that concentration dips, you change statistical probabilities and things. And so there's a couple parameters that fight out and duke it out in the statistics as to which is the actual cause of the end of the reaction. But there are also initiator type polymerization, where you start with something and you have something like an oxygen-oxygen bond. These are pretty volatile. So this is an oxidizing agent, benzoyl peroxide. So anybody that has used any kind of acne cream, it's usually about a 1% solution of benzoyl peroxide. That's just what it is. The reason it works the way that it does is it has this highly reactive oxygen-oxygen bond, forms radicals, goes after, in that case, other biopolymers in the walls, the cell walls of bacteria and fungus, and attack them and does all sorts of things. So radicals do a lot of damage by making and breaking bonds, and that's what happens. So as you run out of these double bonds for the radicals to react with, it'll change format. Depending on how long you allow that reaction to go, you get very long chains. Lots of carbons in dark, lots of hydrogens in light. And polyethylene is just an example of this. It's a very long chain hydrocarbon. And the short versions of this are things like paraffin wax used in common candles. So that is the most common type of wax used for candles. There are some other types, but it's short polyethylene. There are some other types of candles made from things like animal fats that have been rendered down. Basically, what that does is that turns the animal fats into, they break apart based on some chemical reactions that are done, and they leave short chains of these polyethylenes behind from the animal fats. So even those are chemically very similar. And so most waxes are in that category where they're kind of shorter chain based mostly on this polyethylene, carbon, carbon, hydrogens. Start substituting that, and you add in chloride. So the then you can also add in the case of PTFE, or Teflon is one of the trade names for that. That's how we know it primarily. Polytetrafluoroethylene. This gives all of these carbon chains a very high degree of fluorination, meaning lots of fluorines to replace the hydrogen. So PTFE is all fluorines, and once reacted, the fluorine really doesn't care what you think. It's not interested. So if you were looking for a tough molecule, that would be a good analogy for somebody who, for instance, could be shot multiple times or almost multiple times, and almost thrown in prison, and then turned back into the president of the United States or something. That person as a molecule would be most closely fluorine. And the other folks who have a particularly unhinged level of distaste would agree with the letter F as a representation. So every camp wins, right? So polypropylene is another good example of this, where you have these carbon chains and you have a substitution of the methyl group on one of the carbons. So this is a propyl, and it starts as an ene. Now, all of these have enes in the name. The vinyl is indicative of it started with a double bond. So these all have an indicator that there was a double bond. Polyethylene means it was a double bond originally. And many of those repeat units, we end up with single bonds because they're bonded to other carbons. So I don't want that to confuse you, because we taught you a thing, then we taught you that it was wrong, because that's what education does. So these are all double bond entities that then become single bonds in long chains, and that's the way that polymers are made. Polystyrene is an interesting one. It's styrofoam is polystyrene. That's why we call it styrofoam. This is a benzyl ring, so a 6-carbon ring attached as a functional group to carbon, and it has some double bonds. That's what's meant by the circle inside. Polymethyl methacrylate, PMMA. This is some of the clear ultra brittle plastics, sometimes that come in lids. This is very commonly what things like petri dishes are made from. This is has its place for materials. It's not as durable as something like polyethylene or polypropylene. It can be a little bit on the brittle side. Some of that has to do with the fact that it's a partially oxygenated carbon chain. These have these acidic sort of methyl groups that can be reacted away, and so they are not highly resistant to a lot of things. If you were to leave all kinds of really heavy oils and things, you could start dissolving some of these. There's a lot of interesting materials that can happen there. Bakelite, this is an example of phenyl formaldehyde, meaning it has an oxygen and it has all of these um, it has all of these adjacent these are not methyl groups, but they're ethyl groups. So CH2, CH3 ethyl groups. Um, this on a double bonded ring makes for kind of some interesting properties. Anytime you have an aromatic ring is what these are called, a benzyl ring. This is an aromatic compound. So bakelite is kind of an interesting polymer that's not a super heavy, super dense polymer because it has a lot of unsaturated bonds. So there's a lot of free open space in some of those molecules. I don't know how often you're actually interacting on a daily basis with bakelite. You sometimes are interacting with PET, polyethylene terephthalate. This is a type of polyester, ester meaning it has these carbon-oxygen double bonds and an oxygen with them. So esters are interesting. Nylons are a kind of a unique category. So this is polyhexamethylene adipamide, also known as, in this case, nylon 6,6, meaning 6 carbons in the first block. And then this whole thing is a single repeat unit. So 6 in the first block, the 4 plus 1, 2 carbons, 6 carbons in the second block. So a 6,6 nylon is a very common material. This is what a lot of fabrics, various ballistic nylons and things are, I believe, typically going to be about a nylon 6,6, somewhere in that range. So heavy webbing for things like seat belts and so on are where you're going to interact with this kind of material. In that case, they're a woven strand of many, 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 many cords, and as a result, they become incredibly strong. So nylons are very, very useful for a lot of reasons. They don't have a lot of direct oxygen bonding, so they don't have some of the same sort of weaknesses, whereas PET does have some fundamental weaknesses. So you have these carbonyl and a carbonic acid type group, but this one has already been reacted away, so it no longer has the acid form, and it has the ethyl group and then oxygen terminal. So this is what we understand to be the same material as a lot of plastic soda bottles and things are made of. The Nalgene bottles, some of them I think early on were nylon, and I think they switched back to what's referred to as a high density form of polyethylene, because I don't think there were some that were polypropylene in there as well. I don't remember exactly what that sequence was, but anyway. You can see some of these in the visualizer in Wiley. They tend to at least give you some sort of idea of what the spatial relations are between the molecules. I'm not really expecting you to have memorized all of the different polymer chain types. You do need to identify, like, hey, this one looks like polyethylene. This one looks like not polyethylene. But at least as long as you are familiar with what types these are, this becomes a part of the overall solution. So as far as molecular weight, shorter chain means lower mass, lower total molecular weight. The longer chain means higher mass, higher total molecular weight. So low density in terms of polymers is shorter chains. High density is longer chains. And not all of these chains are going to be the same length. There is always a distribution. So the way that we have to test those when we form them often involves generating data for a curve like this. There's some controlled pore size diffusion tests that can be used to determine what your pore distribution or what your average molecular weight distribution looks like. So when you measure it, you get the average, but what does that mean? It's the total weight of the polymers divided by the total number of molecules. You don't necessarily know the total number of molecules always, unless you're controlling very tightly the synthesis. You will be able to measure macroscopically the total weight of the polymers, and that becomes very, very important to know. So there's a number based, meaning number of molecules, so xi times the masses, and then there's a weight based, weight of the molecule times that specific weight of that specific chain times the mass. So this is a weight fraction, this is a number fraction, and a weight fraction is a little bit easier to measure. A number fraction requires you to know kind of some different information. And they will, by number, the number average is going to be higher. The weighted average is going to be lower because it's going to factor all of it into the curve. So a good tightly controlled synthesis has a narrow or a monodisperse kind of pattern. The broader that gets, or the more spread out that gets, the more widely varied the molecular weight, the less consistent the properties of the polymer is going to be. So in terms of the calculations, we took an example here of there was 10 participants ranging from about 104 pounds to 380 pounds. And we want to know what is the average weight of the students based on the number and then based on the weight fraction. So number fraction is fairly straightforward to calculate. The weight fraction is easier in a lot of ways. So when we're looking at this, the first step is to group them into weight ranges so that we can give weighting to the number of students in categories. So we create buckets and put them into buckets, and there's 2, 2, 3, 2, and then 1 down at the bottom. So the total number is 10. The sum of the weights times the averages, because we take a mid-range weight, 110, 142, 184, and a 223, and we re-weight the average that way, and we get the weight-based average. The numeric average is going to be the sum of the NIs, is going to be each NI over the sum of the NIs. So the example in the 81 to 120 pound range is 2 out of 10 for the numeric is 0.2%. But the weighted average is 0.117. So that's why weighted average is lower, numeric average is higher, because of the way that that works on the curve. The weighted average is 2 times 110, so that you're not using different numbers. You're still using the averaged masses in there. So you have 2 times 110 divided by 1881, and you get your 0.117. So the way that this works, the average would be, recalculating this, the 110, 142, 184, 223, and 380 multiplied by our fraction numbers. So our number fractions, the 0.2, 0.2, 0.3, we have to calculate all of those all the way along. So those are weighting factors, gives us 188 pounds for the average. The weight fraction based molecular average weight becomes 218 pounds. So this gives us a pretty significant difference. The average weight of the class being 188 or 218 pounds. So it's important to be clear, especially when reporting these methods. We want to know what was used and what steps were taken to evaluate some of these details, some of the physical properties of these materials. So degree of polymerization, dP, is the average number of repeat units per chain. So we have a degree of polymerization of 6. Why do we have a degree of polymerization of 6? My pen has gone away. That's frustrating. So 1, 2, 3, 4, 5, 6. Degree of polymerization is 6. So the degree of polymerization is proportional to this average mass over the average molecular weight of a repeat unit. So the way that's calculated is we take a chain fraction and a molecular weight of a repeat unit. We sum all of those chain fractions and the molecular weights to get an averaged molecular weight of the repeat unit. That gives us information about some of the physical properties and what to expect in terms of density and how dense the material is going to be, giving it final properties of weightiness or lightweightness, depending on what the application is. So there are different bonding types. There's secondary bonding, which is chain to chain without any actual cross-linking. Then there is branched. And branched becomes these branches sort of entangling each other, and they have offshoots from the main polymer backbone. So all of these red additions are the branches added to the backbone. Then there's cross-linked, when those branches get covalently linked across chains. So cross-linked is the best way to think of something like a rubber band, is an example of a cross-linked chain. When they kind of can resemble network polymerization. This is more like what silicon polymers, silicones are going to be more like network more often than something like a cross-linked polymer. This is part of the reason why they kind of are equally strong in all these different directions, where cross-linked materials are kind of really strong in this direction, less strong in this direction. So they're very directional in their behavior, especially when you add in processing, which we're going to talk about, I think, in I think some of the polymer processing is in the next chapter. So we'll get there. We don't want to do too much jumping ahead because that'll create extra headaches and confusion. So the molecular shape, i.e. the conformation, is what we use to describe the sum total of that. It's chain bending and twisting that's made possible by the rotation of carbon atoms around their chain bonds. So each of these can spin basically freely all the way around, and each of these bonds can spin around each other because they're not constrained, so they can change geometry and flex and wiggle. This is one of the mechanisms that they use to physically store the kinetic energy in the actual chain itself. So when we're bending polymers, when we're doing things at the macro scale, when we're stretching a rubber band, we're causing the polymers to exercise those chains and move around across all of their degrees of freedom. So they can have bond stretching, they can have bond rotation, they can spin around and do all of these things. All of those different ways of moving around are ways that they can store energy by doing all of these things. So you don't need to break chain bonds to alter the molecular shape. Different from metals, because you do need to make and break bonds through the passage of defects through the material, in the case of molecules of metal, to change their geometry and change their shape. So you do have to physically move bonds around. Polymers, you don't have to, they just do that naturally. So there's also a parameter referred to as the chain end-to-end distance, which just gives us some sort of measurement of how far apart the chain's ends are at any given point in time. But the configurations are, in order to change the configurations, you have to break bonds, meaning you can't just, especially in the case of something like this material here. So there are stereoisomers where it can become either this or this. These two are not the same thing because of the geometric reality. This is a tetragonal arrangement. So one peak and a triangular sort of base, and all of these sides are triangular in nature. So A to D to E, right? So this is not pyramid shape where there's a fourth leg in the back and it's a square base. It's a triangular base. So it is a trigonal geometry. But there's a mirror plane that describes this, where now E is on this side. So this is going back into the page. This is coming out of the page. This is in the line with the page. That's the convention for reading molecular geometries. In case that's a detail you guys have forgotten. So these are what are called stereoisomers, meaning there's a mirror plane across which everything gets reflected. If you put one molecule on top of the other, they cannot superimpose. You cannot put this molecule onto this molecule any way that makes it look the same and have the same bond arrangement. So a good example of this is your hands. You have a left hand, you have a right hand. This is a principle called chirality. And your left hand and right hand, if you lay them just on top of each other, you have a thumb sticking out on the left side on the left, you have a thumb sticking out on the right side, then the E is going to be over here and the E is going to be over here. So you got the thumbs out on either side. They cannot superimpose or go on top of each other and cover each other. You have to rearrange the bonds. You have to break them apart and move them around. So those two molecules, even though they're technically the same thing, they are not identical. So they are chemically identical. They are not stereochemically identical. They are stereoisomers. And that's what that means. So the tacticity is another key principle. Stereoregularity or spatial arrangement of the R units, whatever those functional groups are, usually represented as R units. Isotactic means the R groups are on the same side of the chain. And that way, when the chain is rotated in the kind of normal orientation, where these bonds are actually technically going up and down and there's a zigzag, those bonds are all along one side. So they're all coming out of the page. By convention, the way this is drawn, the hydrogens are all going backwards into the plane of the page. Syndiotactic means the R groups are alternating, which means they become next to each other, sort of, except these are actually on the opposite side of the chain. So they are actually not immediately next to each other like this would look. These two R groups are actually physically closer than these two R groups are, because one is coming out of the plane of the page, the other is going into the plane of the page. So they're going two opposite directions. They're not competing for the same space. So don't get confused by that. So syndiotactic, opposite. Isotactic, same. There's also atactic, which is a random mess, which means mixture of all of the above. So atactic is without without an organization or scheme. Cis isoprene is also known as natural rubber. So this is an example where trans-isoprene is something called gutta percha, and it might be helpful to see an example if we've got time. I don't know that we will. We'll see. Might be helpful to see an example of these. These two isomers actually behave very differently. So the hydrogen atom and the methyl atom are on the same side of the chain for cis isoprene. For trans, they're on the opposite side of the chain. So you can see some of these examples of the isomerization using the visualizer, where they're just going to move things around for you to see. One of the final categories of polymers overall, and what have become extremely popular, is the idea of copolymers. So if you can have one kind of polymer that does one thing really well, but you have another kind of polymer that's different, but it can also do something else very well, maybe you want a polymer that can do both things. The idea of a copolymer was born. Although copolymers aren't really a new idea, and they aren't really our idea, because copolymer is really a more accurate description of what a DNA or RNA strand is made of. It is a biopolymer, and it has repeating units, but it's not a random sequence. It's not really an alternating sequence, and it's not really a block or a graft, but it is a sequence that encodes information. So not only is information encoded in the sequence itself, but the physical three-dimensional structures that that geometry necessitates because of the sequence that it is, that 3D folding that it does also contains levels of information, and there's even higher levels of information encoded into the process than that, but that's stuff that our tiny little pea brains can't really comprehend at this stage of the great advancement of science. We've really only barely rolled back the curtain on our own ignorance. So people that tell you all the stuff we know, People that say they know everything probably are the dumbest cats in the room. General rule of thumb. So two or more different types of monomers polymerized together. Random means A and B, no discernible sequence. Alternating mean A and B in order. Large blocks of A units alternating with large blocks of B units. So large blocks, multiples, usually 4 or more. It's pretty common for blocks. Often it's hundreds of units, actually. So it's often very big. Tuning that, adjusting the block ratios helps you to change the parameters. We won't quite get super far into the why behind that. But then there's also graft polymers, meaning something that's been grafted onto another polymer chain. So you have a backbone of type thing A and type thing B. So really, the DNA and RNA would be an example of a grafted polymer, technically, because you have a backbone, and then you have these nucleic acids attached to the deoxyribose chains. So it is technically a graft. It's not really one of these other ones, but it is technically a graft polymer. So we took ideas really from things that already existed in nature, because that's where the wisdom has already been imparted to creation. Somebody was just smart enough to follow along some of the same thought patterns that have already been thought. Crystallinity in polymers. The ordered atomic arrangement involving the molecular chains is pretty key and pretty important. These crystal structures are formed when these polymer chains are rigidly aligned, and they have unit cells sort of like what we see, but they're not as simple as things like body-centered, cubic, or hexagonal. They're very different. So polyethylene unit cells are pretty important and an example of what these chains can look like. The crystallinity, the reason all of that stuff matters, the reason we went through all of that is to understand that they have crystalline regions, i.e. the gray part, and they have folded regions, i.e. the loop structure. So this looks almost like a little polymer Velcro, but these really, really long chains with thousands, maybe even millions of units can fold themselves based on the blocks, because like likes to be with itself. So maybe this region at top and bottom is hydrophilic, meaning likes water, and maybe the block in the middle doesn't like water, so these all align in order to minimize the surface energies around them, and they form these crystalline regions where these are rigidly aligned, and then we have flexing polymer loops of the other type of block at the outer edges that maybe they like water better, or whatever the case may be. So this is a chain folded structure. This is a platelet example with chain folded faces. There can be other examples, but this is just an idea for why we would be interested in creating something like that. The whole idea would be to make a stronger structure than just the polymer chain itself, and use the polymers to make stronger materials based on the organization of higher levels into things like platelets. So organizing a 3D physical structure like this that would assemble itself because of all of the governing thermodynamic energies and the principles and precepts of physical chemistry and thermodynamics that regulate these behaviors. So there's all these other things. So there's a lot of these different kinds of examples of materials that can be made this way. This is part of how cells assemble biopolymers into structures, is by them being built with a specific chemical sequence that imparts these kinds of differing properties that allow parts of chains to align together and form more crystalline-like behaviors. Other parts do not align and don't form. They form loops and other sorts of structures and geometries outside. So often that hydrophobicity or hydrophilicity, whether it likes or is afraid of water, is a good indicator of where something will be. And those same principles and precepts keep bacteria alive. So the polymer crystallinity is important because you'll have regions of what's called amorphous polymer, meaning regions of the polymer that's just loose chains going everywhere. And then you'll sometimes have aligned regions where they are stronger. So the degree of crystallinity is a percentage, and some physical properties, compressive strength, tensile strength, etc., are going to depend on those. And many kinds of polymers have a mixture of these two. So there's differing degrees of crystallinity. If the polymer's aged, if the polymer's been heat treated, if the polymer is thermal cycled too many times, etc. You've all experienced something where you had some kind of a plastic cup or something, says it's dishwasher safe, but after enough dishwasher cycles, it becomes like harder and more brittle, or you drop it and then instead of bouncing, it cracks or shatters or something. There's all sorts of examples of that because the polymer has effectively been aged by increasing crystallinity by heat treatment, because typically you grow and increase percent crystallinity when you heat treat polymers. So lots of thermal cycling does this, and that's what they call aging in polymers. There are single crystals that have been imaged. So this is a multiple layer single crystal that's chain folded layers of polyethylene. And the single crystals are only possible in very, very tightly controlled growth circumstances, but it is possible. So there are also materials that can be semi-crystalline polymers. So they have a nucleation site, they have lots of these aligned domains, and only a small amount of amorphous polymer. And those tie the crystalline pieces together by way of effectively tangling of the chains. Just like if you have a mess of cords, because of all of your different chargers, you pull it out of your desk and 6 cords come out together. It's the same kind of idea. It's that same tangling mechanism. So you can have what's called interspherulitic boundaries, meaning these sphere-like entanglements next to each other, and those tangled tangles of entanglements create the site at which attachment's possible for the growth of these kind of crystalline regions. So the semi-crystalline are what will form what's called spherulite type structures, and that's another kind of geometry that you can kind of see here. They're like grains in metals, sort of. They're not exactly the same, but they can be thought of kind of like that in polymers. And that's why sometimes polymers break and almost look like a metal in a way, but often at the break you'll find some kind of imperfection or something that helped to create that example. So there's typically in optical microscopy a Maltese cross-like pattern on spherulite because of the just physical shape of the geometry. So a lot of information, very important information, but it at least gives you a starting point for understanding a little bit about polymers. We're going to get into some more about polymers in the next chapter, and then we'll wrap everything up with kind of an overview of the things that are going to be on the last exam, so that you guys have an idea what is coming for that. So with that, I want to pause because we've gone just about enough time. Your heads are probably all full now, so we'll catch you in the next one so that we can separate these out rather than trying to overrun and do all of these together.